I don't know which was the first rigorous one. And people had the idea for a while. Maybe the first one was like Aharnav and Ben-Or back in the late 90s. But these first threshold theorems were not very good. I mean, they proved that there exists some tolerable noise rate beneath which you can compute arbitrary reliability, but they didn't give any numbers at all. And if you tried to go through the numbers, you get something like 10⁻⁶ or something. And also, they didn't even work for distance 3 codes. Like the theorems required at least distance 5 before you could even apply them. And so there's some work for a while trying to get a distance 3 threshold theorem. And the nicest paper that came out of this, I think, was this early work by HEP, Alaferis, Gottesman, and Presko. So let me. And this method of this threshold theorem is nice because it works not just for distance 3 codes, but it also gives good numerical results. And there are also thresholds you can get for distance 2 codes in a sense. So distance 2 doesn't allow you to correct errors, but you can still prove a threshold because if you concatenate it, you get a distance 4 code, and that can correct errors. It just gets complicated. Okay, but mostly that's not worth it. So this is mostly for distance 3 or higher. All right. So the idea here is if we want to rigorously bound how much noise our circuit can tolerate, if we want to rigorously come up with a way of modeling noise at higher levels of encoding, this is what they tell us how to do. So what we do is we consider a logical gate, and we consider the error correction before and after it. And so this is called an extended rectangle. So maybe you can see better in this picture. So here I have 2 gates, 2 logical gates, and I have a logical C0. And remember between any logical gate, before and after, we have an error correction. And so the rectangle would consist of a gate followed by the error correction. I'll call that a rectangle. An extended rectangle includes the gate, the following error correction, and the previous error corrections. And these extended rectangles, they overlap. They overlap in this error correction in the middle. Okay. So what they prove is that you can understand the logical behavior of your fault tolerance scheme just by understanding these extended rectangles. And really, most of the time, the most complicated gate is often the C0 gate because it involves 2 code blocks. And so often it's the logical C0 gate's extended rectangle that's the one that's most important for understanding your code, just because it's the most complicated one. So they proved a couple things. Okay, so one thing that they proved, which is maybe less interesting, if you just count the number of locations, location meaning place where a fault can occur, like a gate or a resting qubit, whatever, call that n. And if you distance 3 code, then the effective error rate is going to be at most n choose 2 times p squared. Or if you have a distance d code, it'll be n choose d plus 1 over 2 times p to the d plus 1 over 2. Where p is the stochastic error rate. And this is totally rigorous. That you can show that the tolerable noise threshold then is you just set this equal to p and solve for this equal to p, and so you get p equals 1 over n choose 2. And so if n is small, you're going to get a higher threshold, which is good. And so that generically says to make n small, what you need is your code to be small, or you need very efficient error corrections, fault tolerant error correction circuits. And that'll make the code tolerate more noise. In fact, the proof is nicer than that. In fact, what it says is you can get a better numerical threshold, which is what we call malignant set counting. And so in malignant set counting, here I said any two faults, any two locations that fail is we call that bad. But in fact, it's not necessarily bad. So for example, here, if these two locations fail, that's not going to be bad because I mean this guy is just going to cause a weight 1 error because it's fault tolerant error correction. So you have a weight 1 error here and a weight 1 error on this block. Whatever, that's fine. You've had 2 faults and you have 2 weight 1 errors. That's not going to mess up anything. A bad case would be something like this, like if you a weight 1 fault here and a weight 1 fault here, this fault is copied down, and so now I have 2 faults here, and 2 faults coming into the error correction is corrected in the wrong direction because the distance 3 code, and so you end up with a logical error in this block because I've had 2 faults. That would be bad. And so what we do is we count in a computer. Usually in a computer, we iterate over all pairs of locations, and we check which one of them, which subsets of 2 can possibly cause a logical error on the output. And that's the number of malignant fault pairs. And then what their paper shows is that you can model this as saying the effective noise rate at the next level of encoding is the number of just malignant pairs, which is possibly much less than n choose 2 times p squared. And then you can upper bound the number of triples just by n choose 3 times p cubed. If you want, you can count the number of malignant triples times p cubed, and then you just hit plus n choose 4 times p to the 4th. So this last term is to account for the higher rate errors that you're not counting. But I mean, you can count as far as you have time in your computer to count. Or I guess another thing, instead of counting the number of malignant pairs, what you could do is you could estimate statistically estimate the number of malignant pairs by just trying random pairs and using the random pairs to get an estimate plus or minus estimate for the number of malignant pairs to get some statistical certainty. Right, so you set this quantity, which is an upper bound on the effective noise rate. You set that equal to p. That gives you an upper bound on the threshold. Sorry, a lower bound on the threshold. So that gives a rigorous proof that your scheme tolerates at least this amount of noise. And in fact, for practical for small codes, you can get fairly large rigorous numbers. So this is from a later paper, but they're doing the same thing. So what we've tried here is we have different codes, and each of these codes also comes with its own fault tolerance scheme. So Steen means it's what I just mentioned. You prepare encoded plus or encoded 0. CNIL, it's a different fault tolerance scheme that I didn't talk about. Sorry. But all right, but the same code can have different fault tolerance schemes for how you measure the syndromes of the code. That's why there's 2 of these here. Okay, now what this is the number of locations in the largest extended rectangle. So they looked at all the gates, they looked at all the encoded gates, and they counted the number of locations in the extended rectangle for that gate. And I'm sure, probably sure that I think these numbers are for the controlled not extended rectangle. It's the number of gates in the controlled not extended rectangle. So for example, here for the Steen 713 code, you have 7 C0 gates. Here, let's do some math. You have 7 C0 gates for the transversal C0, and then so what's 575 minus 7? 568. All right, so that's 568, and that should be for 4 error corrections, because the 2 before and the 2 after. So 568 divided by 4 is 142. So 142 is the size. It's the size of 1 error correction for the 713 Steen code, but 1 error correction is a CSS code. So 1 error correction is X error correction, Z error correction. And so 142, that means they're using 71 locations for the X error correction and 71 locations for the Z error correction. It's the same because it's self-dual. And if you dug further, you could probably count and figure out why it's 71, but I don't know. I don't know. But that's what this number is telling you. And hopefully, like if you subtract 9 from this, hopefully you'll get a number divisible by 4 again, or by 8, whatever, you can double check. All right, so then, and one of our entries too would be conservative bound. What they've done here is they've counted at least malignant pairs, maybe malignant triples. I think just malignant pairs to get the bound for, you said p equal to this number here. Okay, and so these are lower bounds. Okay, I'm not quite sure why they're doing that. And here, I think what this is standing for is Monte Carlo. So they're not actually counting all the malignant sets. They're estimating the number of malignant sets by just trying random sets and seeing whether that particular set is malignant or not. And so you'd expect the numbers to be higher, but they're not higher. So I don't know, maybe it's not. Well, it's plus or minus, maybe it is higher and you just can't tell. But basically here, like the advantage of this is you can just, one advantage is you can run it on bigger, larger n. So it's expensive to count malignant pairs and malignant triples and so on. Well, these are high distance codes even. So you have to count up to malignant sets of size 4 for distance 7 code, which is hard if you have 7,000 locations. So 7,000 choose 4 is, I guess, a large enough number. You don't want to do it on your computer. So instead, they don't do it here, but they only do it stochastically. And they get, again, these are the lower bounds and the thresholds. And they're reasonably high numbers, right? So you're getting almost 2 times 10 minus 4 for either of these two schemes, and maybe that one as well. So this is the Bacon-Shor 2515. We talked about the 913 Bacon-Shor code. It's a subsystem code. This is the same thing. It's just you use 5. It's a 5 by 5 square instead of a 3 by 3 square. Yeah, these Bacon-Shor codes are nice. Like you see here, this is distance 7 Galais code versus Bacon-Shor code. So this is a 7 by 7, 49 qubits square, and so they have the same distance, but the Bacon-Shor code has a lot fewer locations to get the same distance. So it's a trade-off, right? So you need more qubits, 49 versus 23, but you get more efficient error correction. And in this case, it looks like the trade-off is in favor of Bacon-Shor, at least based on these numbers. Okay. So that's kind of how that goes. Yeah, okay. I think according to the caption, we've done everything right. Yeah, for a while there's a game like to try to prove the highest number here, and I don't know what the best result now is. Maybe 3 times 10 minus 4 or something. It's not a big deal because here we're only proving lower bounds, and we expect the actual threshold to be higher. And the only way of estimating the actual threshold, I guess, is to just, I don't know, run simulations or something, get a better idea. Okay, so thresholds are known to exist under a number of error models. Here, in this error model, what we're talking about is I think just like stochastic depolarizing noise on the qubits. Actually, I'm not sure that's true. I think actually this error model might be stochastic adversarial noise, meaning that individual locations fail independent of each other with probability p. But if a location fails, the error that's applied can be chosen adversarially. It can be arbitrary, basically. Okay. But there are also threshold theorems that hold for other error models as well. So for example, in principle, you can tolerate leakage errors. So a leakage error means that your qubit has left the qubit space that you're trying to do your computation in. And so that's not a stochastic poly error, obviously. But you can certainly tolerate these in principle. One way of tolerating them is to do teleportation all the time, right? Because if you do teleportation all the time and this cube has been lost, that'll maybe mess up this measurement result, which will mess up this correction, this I, X, Y, or Z correction. But it'll turn a leakage error into a poly error on the output of the teleportation. So, I mean, I'm not sure that that's a good way of doing it, but it's in principle you can always do that to change the leakage errors into poly errors. And possibly it even turns the leakage error into an erasure error if you some way of detecting whether this qubit has left the 0-1 space. Other theorems. So it's known that we can tolerate, we can prove threshold theorems under locality constraints. So for example, if your qubits are arranged in a 2-dimensional lattice and they're only allowed to talk directly to their neighbors, we can still prove a threshold. The way these schemes work is, I think this picture gives you some idea. So like this is a 7-qubit code, 7 qubits arranged on a lattice. And I have 2 ancilla qubits because, I mean, this is just an example, because maybe you need 2 ancillas to do error correction. Okay, so now you can concatenate this on top of itself. So here what I have is I have 9 times 9. I have 81 qubits in this block. And they're arranged in 9 blocks of 9. In each block of 9, I have 7 plus 2 ancilla qubits, 7 data qubits plus 2 ancilla qubits. And then these blocks are encoded ancilla qubits, used for encoded error correction. Then you concatenate the whole thing again, and so these blocks of 81 qubits each is used for level 2 encoded, so 49 qubit, 4919 qubit code states in order to error correct this 7 cubed qubit code. That's the idea. And so the problem here is that so to do fault tolerance with geometric locality, you gotta have like swap gates. You gotta move things around, and that's an issue because at higher levels of encoding, you have to move them farther. So that's why the theorem might break down, but in fact, you can still prove that it does work. So in 2 dimensions we're fine. In 3 dimensions, same thing. In 1 dimension, you actually can't do fault tolerance, sort of. And the reason is because to do interesting things, you need to be able to move qubits around. And so in one dimension, a natural way of doing that is by swap gates. But the problem is the swap gate by itself could be not fault tolerant because a single failure on the swap could mess up both qubits. And that would be bad, certainly if you have a distance 3 code, but even if you have higher distance codes, just moving the qubits around is going to kill you in 1 dimension. But instead what you do is, if we have nearest neighbor interactions, you make this work. So, okay, this is kind of dumb, but it's a fun trick. So what we do is we throw away half the qubits, we just call it an auxiliary qubit in the middle. So between every 2 data qubits, we put a dummy qubit. Now, in order to swap this qubit with this data qubit, what we do is we first swap this guy with the dummy qubit, then we swap, okay, so what do we do? Alright, so, I can't see this. Okay, no, this is working, yeah. So we've next nearest neighbor. So first I swap 1 with 2, then I swap 1 with 3, then I swap 2 with 3. And overall, you can follow what happens to this first data qubit. It ends up down here. This last data qubit ends up here. And so overall, I've swapped 1 with 3. But each of these swaps involves 1 data qubit and the dummy qubit. And so even if 2 of these qubits fail because of this single swap, it only affects one of the data qubits. And so this is fault tolerant. So we're just introducing a dummy qubit in order to make it fault tolerant. And this is, I don't know if it's silly or not. Hopefully you have a 2-dimensional geometry, I guess. or close to two-dimensional geometry. In fact, this next nearest neighbor interaction isn't too unrealistic. For example, if you have I don't know, like a 1.5D architecture where you have a line, then you have another line beneath it, then you can do this. So here, I'm using the first line of qubits as the data qubits. I'm using the second line of qubits as the dummy qubits. And in order to swap these two qubits, I don't swap them directly because a failure there would mess them both up. Instead, I swap this way, this way, this way. And that way you can swap these two data qubits without actually having them involved in one gate ever. Okay, so that's just a